Right. So coming into measuring instruments, there are four instruments that we have to learn about, mainly. Not just four, but there are many. Okay. So we can divide them based on what they measure first. This is just an overview of this part. So we are learning about length measuring instruments, the instruments that measure length. Those are mainly, we have four types. Then we have instruments that measure the mass, mainly the triple beam balance, the four beam balance, and ones that measure the time, the stopwatch, the analog one, the digital one, right? Uh, and we have instruments that measure the angle, mainly the spectrometer, right? As well. So in the measuring instruments lesson, we will be focusing on mainly, we have the meter ruler, which is the basic most one that measures the length, right? Meter ruler, but we there's nothing to learn about the meter ruler. You already know everything. We don't know some things that will, let's say the meter ruler as well. We learn those as well. We have the Vernier Caliper, the traveling microscope, the micrometer screw gauge, and the spherometer. So the first two uses the Vernier principle, and the next two uses the screw principle, right? So basically, those are the instruments that we will be learning, and we will be like just touching through the instruments that measure mass, such as the triple beam balance and the four beam balance, and time and angle as well, right? So before we go into the instruments specifically, we need to know certain general principles that we use when measuring a certain quantity. Okay. So the main word that you will go like find in this lesson is the least count, right? Is the least count. So using the word, you can get the meaning, least count. So what is the least count relevant for? For a measuring instrument. So the least count that the measuring instrument can make, that means the least measurement that it can make, or the minimum reading which can be obtained using a measuring instrument. So it's not just for length or anything. It can be there. It's there for length measuring instruments, for mass measuring instruments, for measuring instruments measuring time, right? Instruments measuring the angle. For every measuring instrument, there's a least count, right? So that is the main concept in this lesson, like the main theory concept that we'll be going through. Okay. And if there's a least reading, there's a maximum reading as well, right? There's a maximum reading as well. That maximum reading is called the range of the instrument. So it can take readings from 0 to that maximum reading, right? So that's the range of a measuring instrument. So the least count and the range are what's most important when determining what kind of instrument that we want to use to measure a specific uh, measurement, to get a specific reading. So like if you want to measure uh, uh, kind of like measure a length, let's say the length of your height, right? You want to measure your height. Compared to that, so let's say you can use a meter ruler for that. But if you want to measure the length from Colombo to Goal, can you use meter rulers? You'll have to use maybe not even 1,000 would be enough, no? You'll have to use, so let's say it's 100 kilometers. So that's 100 into 10 to the power 3 meters. So you'll have to use 100,000 meter rulers to measure the distance from Colombo to Goal, right? So that's not practical. So, I mean, Colombo to Goal distance is measured actually using satellites and stuff. So, going into something less smaller, right? Let's say you want to measure uh, a small distance, like for a small rock or a pebble or a small cube in the range of a few millimeters. You like meter ruler is like this much, the rock is this much. So that's it. Also not practical, and it's kind of difficult to get the reading as well. Difficult to handle the instrument when measuring something that's smaller. So there are other instruments such as the Vernier Caliper that can measure, get the readings for that uh, the rock very accurately and very you can say easy, but more accurately than how, by using a meter rule. So you can see why we need different types of measuring instruments with different least counts and ranges, right? Even the same type of instrument may have different ranges. So there can be, I mean, meter ruler is meter ruler, but you have that small ruler, no, in your pencil cases that has 15 centimeters. So that compared to a meter ruler has a different range, right? So it depends on the reading that you want to take. So you can take different instruments having different least counts and ranges, right? So what is the least count of a meter ruler? I mean, it's the same least count that your ruler, the small one, has. Can you just look at it and tell, just guess, not guess, like look at it and think and tell what can be the least count? Yes. You can see that the minimum reading that you can take, right, between 2 centimeters. Right? I mean, yeah, I can show you this, but like take between 2 centimeters, and you have some lines going through them, no, between 10 centimeters and 11, or between any two given values. There are 10 lines, no. That means 1 centimeter is divided into 10. That means 1 centimeter is 10 millimeters. No? So that's 1 millimeters, the thickness between two small lines. So least count for a meter ruler, or even half meter ruler, or the one that you have is 1 millimeter, right? 1 millimeter. Okay. So that's least count and the range. So again, before going into kind of measuring something, we have to know that like measurements might not always be accurate. Right? So when we measure something, uh, there are different types of errors that can occur, which will kind of reduce the accuracy of our measurement, right? For example, uh, like a simple example would be like if the scale is kind of uh, after some wear and tear, if you can't see the scale properly, you can't get the correct value. And if like the scale is too small also, right? That if the lines are very small and you can't see them, that will also be a problem. So you'll have to use something like a magnifying glass to magnify the scale and get the read. So those are just some basic like practical examples, and we divide them right in our measurements lesson as systematic error, random error, then we have parallax errors and fractional and percentage errors, right? So mainly three types. The parallax is also a type of random error. So systematic errors mean the instrument has a problem, right? So whatever the measurement you take, however correctly you observe and take it, the instrument has a problem, right? So uh, the instrument is what is having the problem now. So like example, let's say the meter ruler, the measurement like this, no? So let's say this is a meter ruler, and they have marked this is 0 and this is 100 centimeters. But That is, let's say the marking that they have given is incorrect, and actually that meter ruler should, the 100 centimeters should be marked somewhere further. I mean, actual 100 centimeters, the length is more than what they have marked. But you don't know that when you take the reading. So all the whatever the reading you take, it will be a wrong one, and we won't even know that it is wrong. Right? So similar to that, systematic errors have fixed values. Right? They have fixed values because they are errors of the instrument. Right? So example is the incorrectly labeled scale. Or like similar to that, the zero mark might be at the wrong place. Right? So like even watches, like even our like watches, since they're battery operated, where the battery is kind of losing power, right? අපි කියන්නේ බැටරි බහැලා කියලා. ඒ වෙලාවට මේකේ තප්පර කට්ට හිමින් යන්නේ. The second hand, the second hand is moving slowly. It's moving slower than a second, right? It might take 2 seconds to go from, like, it's marked like this, the dial. So 0, 5, 10, 15. So from here to here, usually it should go from 0 to 5 in 5 seconds. But when the battery is like powering down, it might take more than that. But you are seeing it as 5 seconds, no? You are saying that it goes from 0 to 5. But if you take like a phone and like start the stopwatch and the watch, see it at the same time, you will see like when the phone stopwatch has like more than 5, this becomes 5 seconds. So that means it's going slower. So it has nothing to do with what we observe and tell, right? It has nothing to do with how we take the reading, right? It's a problem of the instrument. So those are the systematic errors. So the examples for systematic errors are calibration errors, zero errors due to rusting and wear. We will learn them in the specific instrument, so I'm not going to explain what a zero error is, right? And errors due to environment conditions such as temperature and pressure, right? So that is also coming with the zero errors due to rusting and wear and tear as well, right? Wear and tear can occur due to high pressure, right? Wrong usage of the instrument. As a result, it can like deform the instrument. As a result, it might get a systematic error. Okay, so either we have to recalibrate the instrument, right? We have to recalibrate it. Like example, the stopwatch running slowly might be because not of a battery problem, but rather a problem in the kind of the mechanical operation of the stopwatch inside, no? So we have to recalibrate it, give it to a watchmaker and recalibrate it. Otherwise we have to kind of, if it's due to a battery error, just change the battery. Or if it is like due to something, some other fault with the instrument which you cannot correct, you have to replace the instrument, right? So those are the only possible ways that we can prevent the systematic error. So you have to know that it is due to the fault of an instrument, not due to our fault. Okay, fault of the instrument. Right. Then we go to the random error, which is, so there are faults of the instrument and there are faults of the reader or the person that takes the reading, right? So errors due to wrong observation is random error, right? So they are not fixed. I mean, like I can take a reading, the same reading, like let's say the length of a certain wooden block. I'm going to measure using a meter ruler, and I get 59 centimeters. And another one can measure the same length using the same meter ruler and get 60 centimeters. Another one can get 58 centimeters. Another might get 59, right? So, so it changes from observer to observer, right? The random errors are not fixed. That's why it says random. You know, it's random. Random means something that happens like randomly, uh, you can't predict it, right? Random means cannot be predicted. So that means it changes from observer to observer, then that is a problem with the observer. One reader might take the correct observation, someone else might take another. right? So how do we prevent it? So when you take a reading, right? When you take a reading, let's say this is the correct reading in the scale. This is the correct reading. Random error means that the readings taken by observe at different times will be spread around this reading like this. They are spread around it. And they are not like spread towards one portion either. They are spread around it, right? Symmetrically. So how do we get the middle value? We have to take the average of the of all the readings what we get. Right? So in practicals that we do, we always get 2 or 3 values for measurements, either 3 or 6, and then we take the average. So to reduce our random error, right? We are all humans, so that causes random errors. Then we have to take the average in every instance that we can to get the correct, to reduce the random error as much as possible. It might not be the perfect reading that we get as the average, but to reduce it, we need to take the average, right? So when you take the average, this will be the average, right? So this is a very useful way to kind of show how the random error affects the reading. So when you compare it with the systematic error, right? Systematic error, that is, there is a correct reading. This is the correct reading. So due to systematic error, even if we like reduce the random error kind of and observe the reading correctly, accurately, we are taking the reading. It's not a problem of the observer now. The readings will be shifted to a certain side. It can be this side or it can be the other side, right? That is due to wrong equipment. So like if you try to take 5 seconds as correctly as possible, if it's only the random error, no problem in the instrument, it will be kind of with, let's say, 5 seconds, a bit more than that or a bit less than that. So when you take the average, it will come to the middle. But if it's the problem of the instrument where the time is too slow, yeah, when you take 5 seconds, right, where you want to take 5 seconds, you're taking it at it as 5 seconds, but you always get the value as greater than that, right? You might think that is correct, but that is actually always greater than 5 seconds because the watch is moving slowly now. So you're not getting a dispersion symmetrically. You're getting the readings towards one side. So if you take the average from that, that will be somewhere here. So taking the average is not a solution for the systematic error. Right? You can write these some of the points that I'm saying because they are not in the note. Right? You can like go through the note while I'm teaching, right? While listening to and seeing this, you can see that this I haven't written. So you can write these if you want. So systematic error cannot be solved by taking the average of the readings. Only the random error can be solved by taking average of the readings. Okay? Because random error is due to the person. So readers, the observers, incorrect, either incorrect use of the device, or it might be a problem with his eyes. He might not see the scale, right? Uh, but systematic error is due to the wrong calibration or kind of a fault of the instrument, right? So it might be either less than the value, correct value, or greater than the value. It can't be like shifted to both sides. So you can't solve it by taking the average. Only the random error can be solved by getting the average, right? Okay. Now we go to parallax errors. Parallax errors are a type of errors, a type of random errors actually. It's due to the wrong observing portion of the observer, right? So can you see this meter ruler? I'll zoom it a bit. Look at this reading. this meter ruler is having some thickness now. It's having a certain thickness. So as a result of this thickness, right? If you draw it, you can see like this, and consider this as the meter ruler. And there's a measurement that you want to take. Say this is the measurement that you are taking at this point, right? So the scale of the meter ruler is on top, right? It's not on the bottom. When you're looking directly on top, you will get the correct reading. No problem in that. Because like it's aligned now. Your eye, the line that the eye makes with this point is aligned and it's going perpendicular. You're getting the correct reading, right? But if you look at it from the side, right? Your line of sight is towards this. No? So it's towards this. So you are not getting the correct reading. You're getting this as the value, not this one. Then if your eye is on the other side, like at a different place and at an angle, you can see your line of sight is like this and you're getting this as the value, right? So it might be a small error. I mean, not as much as I have shown here. You can see here it's different, right? It might be the, few millimeters also, but it's still an error, right? So to like that's called the parallax error due to wrong observing position of the uh, observer, right? So always when you take a reading, you have to keep your eye at the same level of the reading, right? So to solve it, we use a certain uh, method called the mirror method. That is not usually seen in meter rulers because we can't really use meter rulers. We can't really apply the have a mirror for all meters, right? For meter rulers, the best thing is using a transparent meter ruler, just like what we have. I mean, it's a plastic meter ruler, no? So just like the plastic meter ruler, then we can see what's under there. So you can take a reading clearly, and you will see that. I mean, if it is not the correct reading, like in this one, if it was a plastic meter ruler, right, you will see that you're seeing something like you're seeing this in front of it. The reading and the like the point that you want to take is in front of the reading. So you won't like take the reading like that, and you will know this must be wrong. Then you're observing it correctly, right? So this errors mostly happen when the like in like the meter rulers, right? Because they are wooden. No? Okay, so to prevent it, what we use is the mirror method. So in mirror method, there is an indicator, right, which is used to take the reading, and uh, there is a mirror beneath the indicator. Right? This is the mirror. This one. So this is the scale. This is the scale. The below one is the mirror. Right? So you can see we will be taking the reading, right? When you are seeing this reading, you can see you will see this now. Forget about the mirror now. We'll see what happens when we don't have the mirror. There's no mirror. So when your eye is at this location, you should read 250, this one. So you are going to see that, right? You're going to see that. But like you won't see this point, right? Your eye will be focused on this point. So you will take a reading which is less than 250. And when the pointer is here, right, you will have, I mean, the reflection of the pointer, you will see it away from the, this is the reflection, the one that is on the right side. So your eye will be focused on that, and the pointer will be like at the middle. So you will see the pointer first, but that's at a different value. Here also the same thing. Your eye will be focused on the pointer, but that's at 249. But the actual reading is 250. So, but you can see at that point that the indicator and its reflection are not in the same line. So in the mirror method, we don't take readings when they are separately seen. We only take the reading when they are on top of each other, when the mirror image, right, is covered by the indicator. So then we know that the that we are taking the reading that is directly uh, we are taking the accurate reading, because the mirror image is covered by the indicator. Then they are in the same straight line. We are taking the reading accurately, and there is no parallax error. So the parallax error is very low at that time. Okay. Any questions from that? So you can write down here, mirror method. The readings are taken when the mirror image of the indicator, readings are taken when the mirror image of the indicator is covered by the indicator. When the mirror image of the indicator is covered by the indicator. Right? So that's mostly kind of used in uh, equipment such as the ammeters, the voltmeters, right? So you can write example used in ammeters, voltmeters, galvanometers. We will be learning about those instruments as well, not in this lesson, in the unit 8, right? That you have a long way to go for that. So this is a part of a voltmeter, no? That's why it says 250 capital V volts. Right. Any questions up to now? All right. Okay. Then we go to the next part. That's the last type of error that we have to learn before we go on to this least count principle. So those are fractional and percentage errors. So it's kind of a mathematical thing. Now random errors and systematic errors were not kind of, we didn't have to do any calculations, but we will have to do calculations in fractional and percentage errors. So the basis of fractional or percentage errors is that for any reading, however accurately you may take it, the maximum error for a given reading, right? Maximum error for a given reading is equal to the least count of the instrument. Equal to the least count of the instrument, right? Equal to the least count of the instrument, right? So fractional error, as you can see, is equal to the error that is the least count of the instrument divided by the reading. That is what we call the fractional error. And percentage error will be the percentage value of the fractional error. That is error, or it's better to write it as least count. Least count over reading into 100, right? That is the percentage value of the fractional error. So for us to have an accurate measurement, the error should be less than 1%. Percentage error should be less than 1% for us to have an accurate reading. Otherwise, if it is greater than 1%, it is not accurate enough, right? So, I mean, for a given instrument, least count can't be changed. Least count can't be changed. So if you want to reduce this percentage error, you will have to increase the denominator, that is the reading. So if you increase the size of the reading as much as possible for a given instrument, then you will have the lowest percentage error possible, right? So we have to always reduce fractional errors and percentage errors, just like random errors and systematic errors, as much as possible. So this is just what I said. Okay. So calculate the percentage and fractional errors for the below measurement. So usually a reading is written like this. Reading plus or minus least count. Or there's another way you can write it as well. Sometimes we take the error, maximum possible error, as reading plus or minus half the least count. But mainly we take this, right? You can write this. It's like a common thing for any reading. Like that's how we write it, but we never write it like that in practice. But if they give it like this, that means the reading can be either plus one greater, like up until 1 degree, 1 degree. So this is in millimeters. So it can be between 208, that's plus 1 is 209, minus 1 is 207. So that means that the range for the error of the reading is between 207 and 209. We got 208, right? When we measured, we got 208, but it can be a value up to 209 or can be a value up to 207. I mean, the most accurate reading can be between those two, right? But we got 208. That is what it means when we write it like this. Reading plus or minus these count, right? That's how we write a measurement. So first one, calculate the fractional and the percentage errors. I mean, you don't need to uh, write like get the percentage value. Just writing it as a fraction and multiplying. Keep it simplified as much as possible. Only to take a decimal value, right? Okay, let's send the answers. So for the first one, yes, you don't need to get the fraction. Okay? You don't need to get the decimal place answers. You can keep it as a fraction. So fractional error is equal to 1 millimeter over 208 millimeters, right? So it's 1 over 208. I mean, units get cancelled, it's 1 over 208. percentage error is equal to fractional error into 100. So 100 over 208, you can simplify it a bit, right? Cut both by 2, you get 50, divide by 104, 25 divided by 52. Okay. Yeah, 25 divided by 52 is the percentage error. It's actually 0 point something. What about the second one? Do the second one. Yes. You have sent the answers. Fractional error. Always write what is what. Fractional error is equal to least count 1 millimeter over reading. Reading is 2 millimeters. So that's half, no? 0.5. So fractional error, keep it as a fraction. Then percentage error is fractional error into 100. That is half of 100 is 50%. So is this second reading accurate reading? Can we consider it as an accurate reading? No, right? We can't consider it as an accurate reading. Okay. So either we have to reduce the least count, right? If we reduce the least count, then fractional error will reduce. Or we had increased the reading. Okay. Those are the two only possible options. So if we can't reduce the least count of the instrument, we have to use a different instrument having a smaller least count. So based on that, for a given measurement, right, certain equations are can be based on many measurements. For example, here A is equal to constant K times B to the power X, C to the power Y, and D to the power Z, right? So these are measurements, B, C, and D, not X, Y, Z. B, C, and D are measurements, if they are measurements, right? They are measurements. And those three they have fractional errors, right? So separately you can write, the percentage or fractional error. We'll just take the fractional error for B, that is delta B over B. Here delta something, delta X or something, which that means the least count for that measurement, right? So we don't know whether B, C, and D are taken from the same measurement, or like one can be length, one can be time, one can be mass. No? Well, we don't know that, so we are considering them as having different least counts. So this is the fractional error for B. Then for C, it's delta C over C. For D, it's delta D over D. That's the least count for measuring D. the measuring instrument that we measured D, over the reading. When you consider for A, right, although some are being multiplied, some are being divided, error is error, right? Errors should have to be added. So the errors for B, the fractional errors for B, C, and D will get added when you get the fractional error for A. That's delta A over A. Delta A is like you can calculate A and get delta A, but delta A is just like we are saying it's the least count for that value of A. We don't need to know that. That's just how we represent the fractional error. But there are powers also, right? It's not just B, C, D. B, let's say X is 2, that's B into B. So 2 times the error is there. No? When it is multiplied or divided even, there are 2 times the error. So it's X times B into B, Y times C into C, and Z times D into D. And then you add those fractional errors together to get the fractional error when we calculate for the for the value of A. That's how we calculate the fractional error for the value of A, right? So X is equal to P squared Q to the power half R cube over into S. I mean, the answer is there, but just write it in your notebooks without looking at the answer. How we can denote the fractional error for measurement of X? So we can write it as delta X over X. So they're asking percentage here. So delta X over X into 100 is equal to, that's the percentage of measuring X, is equal to delta P over P, that's the percentage into 100 is the percentage error of measuring P into 2, right? That's the error, that is error of P that affects X, the measurement of X. Plus for Q it's half. So it's half the error, right? Half means it's root Q, right? Half delta Q over Q plus 3 times delta R. That should be into 100. 100 plus delta R over R into 3 into 100 plus delta S over S, that's 1. So even though R cube and S are like they are at the denominator level and not like multiply, right? We take the error as an error. I mean, whatever, whether you multiply it or divide it, error is an error, no? So we add it. So just because we divide it, we don't take minus or anything like that, right? Error is error. So keep that in mind. Okay, we'll do this question. Then we will go into our most basic instrument that we know, the meter tool. You can send the answers after doing. You can just send the fractions. No need to calculate. But like the fraction, simplify, like cut it as much as possible, just like I showed you. Here you will have to get the percentage value also, no? Because they ask, is this device suitable to get the above reading? So it's about a Vernier caliper. We don't know what a Vernier caliper is yet, but that's all right. We can do the questions they have asked. So least count is 0.02 centimeters, and this is used to get a reading of 1.25 millimeter. So first they are asking fractional error. That is equal to least count over reading. So 0.02 millimeters divided by 1.25 millimeters. You get 2 over 125. Right? Multiply this by 100, this by 100. You get 2 over 225. Percentage error. Second one, they ask percentage error of measurement. So that's fractional errors, percentage value. Right? 200 over 125. You can cut by 25. Here, 5. 200 has 8 25. 5 over 8. 8 over 5. For 8, there's 1. For 30, there's 6. So 1.6 you get as the percentage error. So this is greater than 1%. So in third one, they ask, is this suitable to get the measurement? No. Why? Since percentage error is greater than 1%, that is 1.6% greater than 1. Then they ask, calculate the least appropriate or minimum measurable reading which can be obtained using this device. So you can calculate that and send it. Then we will discuss. I'll give you 2 minutes to do that. So in the last question, they are asking if we are to reduce the, if we are to increase the reading, we will get a lower fractional error, right? So they are asking the minimum reading that we have to take so that we will have an accurate reading, so that that reading will be accurate. So what is the maximum error? So minimum reading means for a given instrument, right? Minimum accurate reading for a given instrument, minimum but accurate reading for a given instrument will have the highest fractional error. So what is the highest fractional error that you can have? Highest fractional error without reducing the accuracy. That is 1%. We can have 1% as the fractional error now. When fractional error is 1%, we have a certain reading. That is the minimum reading that we can take accurately. If the reading is more than that, fractional error is less than 1%. Then it's good. But what they're asking is the minimum reading that can be obtained using this device, like for it to be accurate also. So least count we know. That's 0.02 millimeters. Over the minimum reading into 100 is equal to 1% now. Because the percentage error can't be more than 1% for this reading to be accurate or considered as accurate. So reading equals 0.02, this is 1, no? 0.02 into 100. That's 2 millimeters. This is the minimum reading that we should take to consider it as an accurate reading. Understood? Any questions on that? Right. Give me a second to get the question. So we are going into meter rulers. Like we have already discussed everything that's there to be discussed about meter rulers. So it can measure the length, right? You know that it can measure the length. So least count also we found out that it was 1 millimeter, so 1/10 of a centimeter. 1/10 of a centimeter, that's 0.1 centimeter. 1 centimeter is millimeter now, so it's a unit conversion now. 0.1 centimeter in millimeters. How do you do that? 0.1 centimeters to meters. That's 0.1 into 10 to the power minus 2 meters. Meters to millimeters. So that's zero point 0.1 into 10 to the power minus 2 into 10 to the power 3 millimeters. I mean, meter to millimeter is greater value, no? So it's multiplied by 1000. You get minus 2 plus 3 plus 1. 0.1 into 10 to the power 1 millimeters. So that's 1 millimeter is the least count. So you can take it directly. 1 centimeter is 10 millimeters. So 0.1 centimeter is 1 millimeter, right? So errors can be calibration and parallax errors, just like I mentioned before. Right? Even calibration errors, I said no, that the 0 and the 100 mark can be on wrong positions. We won't know it, right? So we will take a measurement using a meter ruler now. So there are measurements, two measurements that we take, L1 and L2 now. So we need to calculate the length of this rod XY. So the value at X is 1 centimeter. The reading at Y is 4.3 centimeter. What is the length of XY? The XY rod. Yes, you can send the answers in the chat. Yes, you can keep in millimeters or centimeters. This is the length, right? So there's a 0 also here. No? So from that 0, this is 1 centimeters, but you can just take the difference in it. So this 4.3 is up until this 4.3 centimeter. 1 centimeter is up until here. So the length is from 1 to 4.3. That is L2 minus L1. Bigger reading minus smaller reading. 4.3 centimeters minus 1.0 centimeters. So we have to write this 1.0 centimeters. Right? Because how we write the reading will give us the value for the least count. Right? So if it because it's zero point 0.1 centimeters is the least count, we have to write it as a, even though it's zero, the decimal point, we have to write it as zero point 0. If we write it as 0.00 centimeters, that indicates that the least count is 0.01 centimeter. So this and this does not have the same least count. If we write it as 1 centimeters, what's the least count? What will be the least count if we write it as just 1 centimeters and no points, no point zero, nothing? What's the least count? Sorry, least count, not least. What's the least count? I gave the answer already. No? So 1 centimeter is the least count. Then. No zero, no? 1 centimeter is the least count. Right? So when least count is 1 centimeter, if the reading is let's say 10 centimeters, you just write 10 centimeters. If the least count is 0.1 centimeters, it's 10.0 centimeters. It's like that. Okay. So by just taking the reading, you can identify what kind of least count it has. Right. So here the reading will be 3.3 centimeters. You have to write this as 3.3, not 3.30. 3.3 because least count is 0.1. Right? Because you can't take a reading less than that. If you write as 0.30 centimeters, that means the least count is 0.01 centimeters. That's 0.1 millimeters. You can't measure now in what's the definition of least count? It's the minimum reading that can be taken by an instrument. So if you write it as like this, it indicates that the least count is 0.1 millimeters. But you can't take that measurement practically in a meter. It's 1 millimeters for the least count. So this will be wrong. That then you have to write it properly like this. Right? To one decimal place if it is in centimeters. If it is in millimeters, you have to write 33 millimeters. You can't write 33.0 millimeters. Because if you write it like that, then least count is 0.1 millimeter. But that's not so, no? Least count is 1 millimeter. Okay? Right. So we are going into the Vernier principle. Right? We are going into the Vernier principle. That we need a nice diagram. So in Vernier principle, I have a video also that I want to show to you, then you'll understand it very nicely. So there are two scales. So let's just go to Vernier Caliper. Yes. Here. So this is a Vernier Caliper. I mean, Vernier Caliper is the instrument. Vernier Principle is another thing. So Vernier Caliper is used in the traveling microscope and the spectrometer as well, right? The Vernier Principle is used in many instruments. So Vernier Caliper is what we call this specific instrument that uses the Vernier Principle, right? Caliper is the shape of the instrument that we have shown. So you can see in this instrument, just don't focus on the instrument, focus on the two scales. You can see there are two scales, right? In a meter ruler, there will be only the main scale. But here you can see there are two scales. So here, this scale, the larger scale is called the main scale. This is called the main scale. And this is called the Vernier scale. Oh, here Vernier graduation means not graduation. Vernier scale. right? That vernier scale is very small and it only has around, here you can see 0, 1, 2, 3, 4, 5, 6, like that, and there's a middle division as well. So it's actually like 20 divisions here, but most of the vernier scales will have like 10 divisions in the vernier, right? 10 divisions in that vernier. So here, when the jaws are shut, this is movable. This part is movable, right? It is slid along the uh, main scale using this thumb grip. I will show you a video, right? Otherwise, I mean, I'm just cutting banaki now again. I'm just speaking from only the mouth. I'm not showing you. So here is a picture where the vernier scale or the jaws of the vernier caliper are shut, or they are opposing, or they are at like close, as much close as possible to each other. They are together. So at that time, in a proper instrument, the zero of the main scale and the zero of the vernier caliper should align properly like this. They are aligned like this. One line should be at the zeros. Then you can see that this much, this is the vernier scale up until 10 divisions. So you can see at the 10th division that there is a certain main scale division. That's actually, so this is 1 centimeter, that is. So you can see this is the main scale uh, least count. That's 1 millimeter. So how many millimeters or how many divisions in the main scale are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? 9. So I'll just use this using, explain this using, not using actual values, but rather it's easier to explain using some variable. So let's take our least count as A, right? Least count is A. And n divisions of the vernier scale, right? N divisions of the vernier scale are here, right? So if n divisions are here, we can see here, I mean, it's like 10. Here it's 10 divisions. Here it was 1, 2, 3, 4, 5, 6, 7, 8, 9. That is, if it's 10, it's 9. That means if it's n, it's n minus 1. N minus 1 divisions of the main scale are divided into 10 divisions of the vernier scale, right? So that's 9 millimeters is divided into 10 divisions of the vernier scale. So what is the size of a vernier scale division in terms of not in terms of the variables given? What is the size of a vernier scale division? Least count is A. N minus 1 divisions of the main scale divided into n divisions of the vernier scale. Yes. Uh, Values that you have sent in numbers are correct, numerical ones. Using n minus 1, n and a. So n minus 1 is the number of divisions in the main scale. Least count is A. Then you can find the total length of the main scale, that is divided into n divisions in the vernier. So you can find the total length of the vernier. You can find the vernier total length of the main scale divided into the vernier. That is A times n minus 1, right? N minus 1 was the number of main scale division. If it is 9 and the least count is 1 millimeters, it's 9 millimeters, the total length. So it's A times n minus 1, right? Then, so one main scale division is A, right? That's one main scale division. We are going to find the length of one vernier scale division. So the total vernier scale is total vernier scale range. That's A times n minus 1, this much. This is A times n minus 1, right? That is divided into n divisions. That is divided into n. So if it is n divisions, that total length should be divided by 10. නේද? දැන් ඔතව 9 millimeters තියෙනවා ඒක 10කට බෙදනවා, right? So that is 1 will be 0.9 millimeters. Then similarly, if the total length is A times n minus 1, right? The length of one vernier scale division will be A times n minus 1 divided by n, right? Divided by the number of division. Okay. So least count in the vernier scale is described as the distance that the vernier scale must be moved, in order to coincide two lines in the vernier scale and the main scale. The minimum distance that it should be moved. So vernier scale now is being separated. These are called the jaws, right? Maybe jaws of the vernier. They are now being separated. Vernier scale is pulled back. So the minimum distance, it must be pulled back in order to coincide a line of the main scale with the vernier scale. So minimum distance would be for this division. First division එකට තමයි minimum. So how much does it have to be moved? So this is value of one main scale division. This is the value of one vernier scale division, right? This is 1 VSD. This is A, right? That's one main scale division. So their difference is equal to the value that has to be moved in order to coincide these two lines. In order to coincide these two lines, right? That difference is the difference between one main scale division and one vernier scale division. So that is the least count of the instrument, right? That is the least count of the instrument. The minimum distance that the vernier scale has to be moved to coincide main scale division with the vernier scale division when both are from 0. So one main scale division is A, one vernier scale division is A times n minus 1 over n. So you get, so this total one is, also A minus 1, right? One vernier scale division is that total length divided by n. So common denominator n, right? So you get an, this will be multiplied by n, this multiplied by n. An minus open brackets, an plus a, no? Minus a into minus 1 plus an plus 1 over n. So you can see an and an minus n is 0, plus 1, plus a over n is equal to the least count. So you can write least count is equal to a over n. Least count equals a over n. Then A is the least count of the main scale. N is the number of Vernier scale divisions. Least count of the main scale divided by number of Vernier scale divisions is the uh, least count for the instrument, right? That's the least count for the instrument. So you can see the main scale has a separate least count. It's just like not it's just like in a meter or 1 millimeter. But what we have done by applying the Vernier scale is that we have reduced the least count for the whole instrument, right? So there's a way that we have to take the reading, specific way. We have to take the reading using this Vernier scale as well. We will go into it next. Did you understand how the least count is calculated for the Vernier scale? Just a theory. We will do a lot of sums, right? This part is given in the page uh, uh, before this page. This is not given. If you want, like you don't need to draw a Vernier scale. You can just draw this scale part, the main scale and the just the scales, right? If you didn't understand, just tell me. I will explain. Okay, great. It might be a bit confusing to understand at this point, like when we like were first initially trying to get to the idea of the least count of the instrument. I mean, by the end, it's mostly okay. So I would like if you all draw this part because like we won't be coming back to that again and again. That's the theory, no? You can draw it like on a side of the same paper. There's I think space on the page before the bottom part here. Even I think you can draw it like that, like this. You can draw. So this reading should be like here is the first reading for the Vernier 1. This is 0. This is also 0. Right? This is the ninth one. It's not the 10th reading. So it's n is what is usually 10. So n can be 10, 20, 100, right? N is not a fixed value. I'll give you 2 minutes to just do that. We will go into the different instances that we use this, right? I will show the video, then they will, yeah, it's there. So a general equation we can write that the least count is equal to one main scale division. That's the least count of the main scale over the number of Vernier scale divisions, right? But basically we use A over N for most of the Vernier principles. Yeah, I will be going through like for this lesson we don't need to do any practicals. If the practical book is anyways covered when we do the lesson first for practicals. We don't need to do them again, but like specific for lessons, I will be doing the practical. Right. So you can see here that is the what I told. So this you have to remember, right? This is important. The distance with which the Vernier scale should be pushed forward to coincide Mark 1 of the Vernier scale with Mark 1 of the main scale. That means the first mark, right? There's no numbering as Mark 1. Okay, is the difference in length between one part of the vernier scale and one part of the main scale. Right? It's better shown using a visual representation, just like we did, rather than don't just study this. Understand and remember this. What the least count is. Okay, that's the least count for the instrument. Okay, least count for the vernier scale is one vernier scale division divided by the number of divisions. Vernier for the least count for the main scale is uh, one main scale division. Sorry, least count for the vernier is 0.9. No, let's not go there. So for the main scale, its least count for the main scale is one main scale division. Least count for the vernier scale is also one vernier scale division. One vernier scale division was a n minus 1 over n. This is least count for the vernier scale. Right? Least count for the instrument is a over n. That's least count of the main scale over number of vernier scale divisions. Right? So this is important as well. Differentiating what the least count of the instrument means. Right? Vernier scale has a separate least count. We don't need that. Right? I mean, that's useless actually. If you want, you can write these like points. Right? These are like can ask in MCQ sometimes, but like it's easier to understand. Like mostly we get least counts, the percentage fractional errors in structured questions. Right? Find the least count. Find the least count, then we go see how we take readings using a Vernier. You can send the answers. Now, before going on to how to take the reading, we'll do a few least count questions. Yes, so you have got the correct. So you can here can see 9 divisions of the main scale are divided into 10 divisions of the vernier scale, right? So our least count is that is equal to least count of the main scale or main scale division over number of vernier scale divisions. That is A least count of the main scale divided by n, number of vernier scale divisions. Least count of the main scale is 1 millimeter. N is 10. So you get 0.1 millimeters as the least count of the instrument. So like the vernier scale division is 0.9 millimeters, right? So you can't really see that least count anywhere, like looking at the scales, right? It's the, like when you separate the jaws, push the vernier scale back, and the first line, this first mark coincides with the first mark of the vernier scale. You can see there's a small gap, no? Then you know that distance between the jaws now is equal to that gap because it has now coincided. That means it has moved across that gap. That gap is equal to the difference of this main scale division and a vernier scale division. So you can calculate it using the main scale and the vernier scale. We'll see that next. That is why we say the least count is equal to that difference. That is, for this one, it's 1 millimeter minus 0.9 millimeters. No? You get that also zero point 0.1 millimeters. You get the same answer, right? Least count is equal to the difference of the one Vernier scale division and one main scale division, right? Right. We'll do a question. I gave the question to separate. Do the second one. Do the second one and send the answer. Right. Done? Okay, that's all right. Take your time. Always write units when you calculate answers. So main scale has 1 millimeter divisions. Vernier scale has 20 divisions which coincide with 19 divisions of the main scale. So you can apply this equation. The equation is there in the tube, in your tube. Here, the equation is there. That's why I told you to write the equations. It's your duty to write the equation. So A, now here there are one main scale division is 1 millimeter. That is simple A is 1 millimeter. Vernier scale has 20 divisions, right? So that's N. So you can, they are asking length of one vernier division. Now 19 divisions of the main scale, that is 19 millimeters of the main scale are divided into 20 divisions of the vernier. So 19 millimeters divided into 20, right? So that will be the length of one vernier division. There are not less than 20, I know. I mean, you get the idea, right? So 19 millimeters divided into 20. So one vernier scale division is 19 over 20, that's 0.95. So 1.9 over 2, 0.9, that's 18, 1.95 millimeter, right? That's one vernier scale division. They are then asking to calculate the least count of the vernier. Least count is equal to one main scale division minus one vernier scale division. Or you can just apply A over N as well. So here one main scale division is 1 millimeter. One vernier scale division we just found out 0.95 millimeter. So 0.05 millimeter. You can use this to confirm. Least count equals A, that's 1 millimeters over N, that's 20. One means A means main scale division least count. Right? So 1 over 20 is 0.05 millimeters. Not millimeters, point, yeah, 0.5 millimeters, 0.05 millimeters. So this is applicable, the A over N is applicable when the difference in the main scale and the least vernier scale divisions is 1. Right? Difference between the main scale and the vernier scale divisions, number of divisions is 1. So if 19 is divided into 20, if 9 is divided into 10, if 49 divided into 15, 99 divided into 100, like that. And for example, I'll show you why I'm saying it. Same question, let's do the same question. Main scale of a vernier caliper has 1 millimeter divisions. Vernier scale has 20 divisions which coincide with not 19 divisions, right? Not 19, with 9 divisions. Now it's 9 divisions. So you can like just write with a star number of vernier scale. You can write the data. You know the question, same question. You can write least count of the main scale is 1. Here this one. N is also still 20, but for the main scale now, it's not 19 millimeters. It will be 9 divisions. No? It's 9 millimeters. 9 millimeters divided into 20 millimeters of the vernier. Calculate the length of one vernier division. Calculate length of one vernier. So I hope the initial question that we discussed is all right. So here it's not 9 millimeters. I mean 19 millimeters. Yes. Everyone has, both of you have got the vernier scale division value. So one vernier scale division will be equal to the total length, that is 9 millimeters divided into 20 now. No? So 9 over 20, that's 0. For 90 there are 4, then it's 80, 10, 400 there are 5. 0.45 millimeters. So find out the least count now. You get a weird value. I mean, can't really be considered as a proper least count. But just to show what I want, I use that. What do you get as the least count? Which equation can you use? The definition matters. It's the minimum distance that the least count the vernier scale should be moved to coincide the first mark with the first mark of the main scale. So it's actually the difference between one main scale division and vernier scale division. Because if this is 0 and 0, same line. Like this. So this is the first mark of the vernier scale. This is the first mark of the main scale. This is one vernier scale division. This is one main scale division. So the difference is equal to the distance that the vernier scale has to be moved. So it's one main scale division 1 millimeter. Yes, both of you have got it. One vernier scale division is 0.5 millimeters. So you get it as 0.55 millimeters, right? So if you apply A over N, just see 1 millimeter is A, these count for the main scale, that doesn't change, and N is 20. You get 0.05, right? That's incorrect. So this A over N is only applicable when the difference between the number of main scale divisions and number of vernier scale divisions is 1. So 19, initially it was 20 and 19. So that's 1, right? So it is only applicable at that point. You can write it in the theory, right? Where the equation is there, A over N, here, page number, here this one, page number 4. So you can write it there by putting a star. This equation, this one is valid, okay? This is valid for anything. This is the general equation, but this is what we use because like it's easy, A O N, right? But first we have to see whether the difference between the number of uh, main scale divisions converted to the number of vernier scale divisions, their difference is 1. So you can write that down. Difference between the main scale divisions and vernier scale divisions should be 1. Only applicable when the difference is 1. All right. I think getting readings using the Vernier Caliper will do next day. Well, that's a bit of an important part. We'll do another sum. So now we've finished basic math, so no need to spend time on that now. We can cover a bit more, like a bigger portion of theory every day. Right. I'll erase this. Yeah, reading will do next day because I need to do questions, few questions, taking the readings of the Vernier scales properly. So for homework, right, this same second question, take the number of Vernier scale divisions to be 10, right? For homework, take the number of Vernier scale divisions as 10 and the number of divisions on the main scale as 19. Yeah. Right? Vernier scale now not 20, it's 10. Like that's for homework. Then also do the fifth one. Homework. Right? Fifth one homework. And the sixth one also. 5, 6. So 5, 6. Let's see whether I can give you. This was 10th one and 8th one. So what are the questions I gave? I'll tell them. 5, 6, 8, 10. and also the modified version of the second one. That's enough homework, or do you want more? Okay, so that's enough then, right? We'll do the class next week, I guess. I mean, no time to do a theory part either, and no point in doing these sums in the class. It's better if you can do them at home. So try them, okay? Uh, right. Any questions from what we did today? Revise the least count theory and come before you come for the class next week, because you will forget it in 1 week. How that A came, how the what is N, what is Vernier scale division, what is main scale division. You will forget all that. ඒ ඔක්කොම අමතක වෙනවා ඊළඟ සතිය වෙද්දී. ඒ නිසා මේ revise the lessons properly, right? And come revise this. It's a small bit of theory. Now it will take 15 minutes. And come for the next day. So next day we will finish Vernier calipers, and also I think traveling microscope also we can start. We don't have that basic math part now, no? Right. So we will continue the class for next week. Yeah, thank you. Right. Okay. So have a great day then. We will stop for today. Right. Bye. Good night.